Our solar system is a wondrous place with a single star, our sun, and everything that orbits around it, planets, moons, asteroids, and comets. What do we know about this beautiful solar system we call home? It's part of an even larger cosmos with billions of other solar systems.
Hi, I'm Jim Green, Director of Planetary Science at NASA, and this is Gravity Assist.
And I'm Lori Cantillo with the Science Division here at NASA headquarters, and we're going to do something a little different today to launch Season 2 of Gravity Assist. We're talking about mind-blowing science discoveries, and one of them happened 60 years ago with our Explorer 1 mission, which revealed these intense radiation belts that we have around Earth. They're called Van Allen belts. It's a cool story, so to tell it, we're going to turn the tables on our host, Jim Green, and find out about his gravity assist. That's the term we use to describe an event or a person in your life who helped you figure out what you really love to do and forever changed your path in life. So, Jim Green, what was your gravity assist?
Well, thanks, Lori. You've done a fabulous job helping me with our Gravity Assist interviews over this first season, and I'm delighted to be able to kick off the second season and talk about some of my experiences. My Gravity Assist really started in high school. I had a high school chemistry teacher who ended up with the keys of an observatory, a donated telescope. Turned out it was a 12-inch Alvin Clark refractor. And for you amateur astronomers out there, I'm sure your jaws have dropped. And
they still make those?
No, Alvin,
I didn't think so.
Alvin has gone out of business.
Oh.
But I think this was made in probably the 30s.
Okay.
Yeah, in the 30s. 1936 or so, I think, is when it was made. But this particular telescope, fabulous telescope. I had it at my beck and call for a couple years in high school. And I made instruments for it. I studied stars. I studied the planets. I took pictures that ended up in Sky and Telescope. And I took images of the sun every day for 3 months during one summer and 3 months during another summer. And so at the end of my high school, I knew exactly what I wanted to do, and that was get into college and get a degree in astronomy. But that didn't end there. You know, many of our scientists, as you've heard in many of our other podcasts, they've had multiple gravity assists along the way. And my next one really started my first year at the University of Iowa. I was born and raised in Burlington, Iowa. It's just a small town on the Mississippi, and University of Iowa was one of the big universities in Iowa. And I took Astronomy 101 with about 400 other students.
I know what that's like.
Yeah, I mean, the place was packed. I walked in the first day, and and the only places available were up front.
Uh-oh.
Yeah, so I had to sit
That's what you
in the
get.
front. Well, I always enjoyed sitting up front. I wear glasses, and so my eyes aren't really that good. So I would indeed sit up front. But it was taught by James Van Allen. And
Whoa, the
James Van Allen, and we'll learn more about him because indeed he was the first investigator of our first experiment ever in space on the spacecraft Explorer 1. So at the end of first semester of Astronomy 101, I got an A. Thank goodness. There was only
you better have. Planetary science director getting less than an A. I don't think so.
Well, I wasn't always great in school. The ups and downs happen, and we always have to remember you gotta stay the course. But second semester, I had an opportunity to take a small two credit hour course. And so I took readings in astronomy, and it was taught by staff. That's what it says in the course catalog. And so when the course started at a designated time in Van Allen Hall, room 10701, I went to that room, opened the door, and it looked like a warehouse. It was this huge room, printouts all over tables, magnetic tapes, and bookcases, and a cluttered room from that perspective, a storeroom. That's what these rooms were storerooms. And I'm standing in the doorway, going through this course catalog, figuring out I must have messed up.
Wrong place.
Wrong room.
Wrong
right?
time.
Right? And so for behind the bookcase, Dr. Van Allen said, Jim, this is the place and you're my only student. And so instead of being taught by a grad student, I had a full semester with James Van Allen. And when he found out that I had taken pictures with an Alvin Clark refractor, and in particular the solar set, it was during solar maximum in the late 60s, early 70s, and he said, wow, let's do some things. Let's do some research with this data. And I go, research? Wow. What's research? So we talked about it. I showed him the data. He loved it. And the big suggestion that came from him is why don't you look at how fast the sun spins? Let's do that by looking at the sunspots and how long it takes for them to go around. And indeed, I had plenty of data to make measurements of a solar rotation, and I did the same research that had been done about 70 years earlier and wrote a science paper, just, introduction and discussions and abstracts and all the stuff, components of a paper, and he was the referee. And so at the end of that semester, indeed, I knew what research was all about, and that gravity assist was absolutely unbelievable.
It's cool how many people will cite teachers as being that gravity assist, and good for you. Well, I'm certainly glad that you took that class.
Yeah, me too. But that connects really well with what this year is all about. This is the 60th anniversary of NASA, okay? And it really kicks off with our first successful spacecraft called Explorer 1. Now, you can get online and you can probably go to some of the images that the National Air and Space Museum posts, and you can see what the Explorer 1 rocket looks like. It's about 2.5 stories tall, and it's a huge, beautiful rocket that had on top of it an experiment, a Geiger-Müller tube that looked at cosmic rays, and that was Van Allen's experiment. And on the side of it are two letters. Two huge letters painted on the side, U and E. And so everyone knows about it. You can see it's very distinctive, and that's the way that goes. But I finally found out the story behind UE.
Yeah, like why not U and S?
Could have been. Here's how it goes. After I graduated from the University of Iowa, I ended up at Marshall Space Flight Center at NASA, which is one of the 10 NASA centers. And it's a fabulous place. They do all kinds of things. This is where von Braun was, and they were building a series of rockets. So Van Allen came down. I invited him to give a talk, and then I had a big reception over at my house. And so I had scientists and engineers from the center, and I was walking around with a tray of hors d'oeuvres. Okay, so I walk up to Van, and many of us students called Dr. Van Allen Van. It was a very endearing term, and he loved it. Never batted an eye over that. And so I walked up, and there Van was talking to one of our engineers. Actually, it was my next door neighbor, Jack Wade, who worked with von Braun. And I'm standing there. Would you like an hors d'oeuvre? And Jack says, Dr. Van Allen, do you know what UE means? So wow, I had to hear this, man.
Yeah, no kidding. Great time.
Yeah, great.
To be there.
I had seen UE, I don't know how many times, but I didn't know what it meant. And Dr. Van Allen said, no, I don't think I ever knew what that meant. And so Jack says, well, here we are in Huntsville, Alabama. This is where the Redstone Arsenal is, and currently the Marshall Space Flight Center sits on that. But Marshall hadn't been put in place at that time. And so Jack said, there are 9 unique letters in Huntsville, and U is 2 and E is 9. And so UE is a code for a number 29. And Van Allen said, well, why didn't you just put 29 on the rocket?
Yeah.
Just paid 29. And Jack said, well, we didn't want to do that because if we put 29 on the rocket, the press would ask us what happened to the other 28.
1 through 28. Yeah, that's a good point.
And the problem with that is they all blew up. And so Van looks at me and I look at him and I'm thinking, thank God UE didn't blow up.
Yeah.
But that's the way it was early on. We were struggling in this nation to be able to build rockets that work and get things into space. Sputnik had been orbiting the Earth for months earlier. The USSR was celebrating their launch of Sputnik, which occurred on October 4th. And that was last year's celebration. They had their 60th. So in 1957, Sputnik went up, and here we are in 1958, January 31st, Explorer 1 takes off and gets into orbit. What a fantastic time that was. I mean, the press conference was something like 2:30 in the morning at the National Academy. Wow. And that's the very famous picture of, you see Dr. Van Allen Pickering from Jet Propulsion Laboratory, which helped build the experiment and integrate it into the rocket, and then of course von Braun, which got the rocket into space.
Wow. And they're holding it over their head.
They're holding it over.
And it's, how heavy is that
Well,
thing?
that's the third stage. Mm-hmm. Yeah. And the experiment is inside that.
Okay.
And so you had several stages that are a couple stories tall just to get that little bitty thing into space. Yeah.
Wow. That's what really launched the space race,
it
too.
Did.
And the whole era. That it was, in a sense, the competition that really inspired and got people going. But then the fascination that the American public had with space exploration really took off.
Yeah, Explorer 1 was our first successful attempts. And what we found out immediately is that it had things to teach us. The data came back. Van Allen also had several other explorers over the next several months to get additional data. And by May of 1958, he was announcing the results of those several instruments, those Geiger-Müller tubes from Explorer 1 through Explorer 3, since two didn't make it into orbit. So Explorer 1 and Explorer 3 told us that there was a set of very high energy particles racing around our magnetic field above our atmosphere. And that was the radiation belt. We call that now the Van Allen radiation belt. So
what was that a total surprise, or did we kind of theorize ahead of time that there was something going on like that?
Yeah, for most of the scientists, I would say nearly everyone, it was a huge surprise.
like so many things.
Yeah. Now, you would think that there would be some basis for understanding that we would expect to see the particles trapped, and there was some of the earlier ideas about how particles and magnetic fields interact. If you have a magnetic field, it can trap charged particles. They have a tendency to spiral around the magnetic field and don't leave the environment, don't leave the area, and so they can hang around for long periods of time. And in fact, there's hints from other planets that they have magnetic fields. And that had been going on for many years prior to this.
So it's a good thing that Earth has these magnetic fields, correct? These are what protect us from all of this space weather, from radiation, from the solar wind. And did we understand that back then at that time, that's what was the significance of this finding?
No, we didn't. We absolutely did not. It is important that this Earth has a magnetic field. The magnetic field does trap charged particles, and as the sun heats our atmosphere to the extent where the atmosphere can actually become disassociated into charged particles, then and actually evaporate into space, then the magnetic field traps those. And so we have evaporated atmosphere that we call the plasmasphere. It starts out in the ionosphere and goes out into space, and it creates another region called the plasmasphere. And that allows us to hang on to our atmosphere for long periods of time. So that's just one effect that the Earth's magnetic field, and that includes all the other planets that have magnetic fields too. That happens to them. Mars, it lost its magnetic field, and now we know that the solar wind, as it has continued to strip atmosphere out of Mars, and in particular the oxygen, that is disassociated from water, from H2O, and the O gets transported and then stripped away, has really changed that planet now into an arid and dry place.
I find that story fascinating that scientists now believe that Mars was, back then a very warm and wet environment. That we see evidence of canals and flowing water that once was on the surface of Mars. And I guess the obvious question is, do people wonder if this kind of process could happen here on Earth, for example? Are we studying that as well?
Indeed, we do compare our planets. Venus is another one that's Earth size. It doesn't have a magnetic field. And although its atmosphere is extremely dense, it's largely made up of carbon dioxide, where we have only a very small percentage of carbon dioxide here on Earth. The biology of our Earth has really taken hold of the atmosphere, and now the atmosphere is dominated, although it has a lot of nitrogen, but the oxygen that life produces is really the critical change and difference than what's happening on Venus. But Venus has so much atmosphere. The stripping that goes on Venus pales into comparison to what's being generated, probably from still active volcanoes that are going on.
Well, and then Jupiter, of course, the king of the solar system, has just these intense radiation belts. How did those on Jupiter compare with the ones on Earth, and what did NASA have to do to protect our Juno spacecraft?
So indeed, Jupiter, we've known something was going on with Jupiter very early on, before Explorer 1. Bell Labs had taken radio dishes out to explore how we could use radio frequency light for communication. And as they were doing that, they saw two bright things in the sky, and they figured out one was the sun and the other was Jupiter. Well, the radio emissions from Jupiter were coming from the trapped particles in the intense magnetic field, and they were coming from the Jovian radiation belts.
Wow.
And that field is more than 20 times stronger than the Earth's magnetic field.
Mm-hmm.
So it's pretty intense, and it therefore holds very close to the planet some really intense particles that spiral back and forth along the magnetic field lines. And so that hurts our spacecraft. These particles move so fast, they actually will penetrate the skin and get into the circuits and really cause some problems if we don't take that into account. And Juno has that. Juno's got some
like
really,
a bank vault, sort of.
It's got this huge vault. That's right. So we built this bank vault, if you will, and put all our sensitive electronics in that, and that seems to be working well for us.
But has the discovery of the Van Allen belts changed, for example, how we might want to launch a rocket? Has it changed how we explore space?
No, it really hasn't, in the sense that in planetary science, if there's a place we need to go and we have to go through the belts, we know how to do it. Mm-hmm. And so when we launch and our spacecraft will zoom right through it, typically we'll keep all of our experiments off. We'll make it through the belts, and then we'll do the checkout as the spacecraft is cruising in the solar wind.
You touched on something that since coming to NASA has really made an impression on me, and that's how interconnected all the science is that we do, that what we learn about Earth we can apply to what we're studying on planets like Jupiter and Venus, and vice versa. So it really is important that we look at all of our planets, and that by looking at other places in the solar system, we can therefore learn about what might be Earth's future.
Absolutely. The concept that the magnetic field was important to maintain our environment, in particular our atmosphere, is really something that we really understand because of Mars and our study of Mars. And so then when we look at Venus and we see, well, Venus doesn't have a magnetic field. Why doesn't it have a very tenuous atmosphere like Mars? And so now we have to probe and look for other explanations, and we do. We find out that Venus is incredibly an active planet, probably longer than Earth has been in terms of its volcanic activity for whatever reason, and we really don't understand or know that. And so it has dumped an enormous amount of CO2 gases, and we believe it may still be active today doing that.
Now, we have actually a moon in the solar system with a magnetic field. What's going on with that?
Yeah, well, that's a really neat moon. It's not our moon, although we know enough about our moon to realize that it probably had a magnetic field early on in its history. But there's a moon at Jupiter. It's called Ganymede, and it has its own magnetic field. Now, what's really spectacular about Ganymede is, we think of moons being smaller objects. Ganymede is huge, and Jupiter is, the big planet in our solar system. But just to give you an idea how big Ganymede is, it's bigger than the planet Mercury. It is the largest moon in our solar system, and it generates its own magnetic field. And so it's also has another unique characteristic, and that is it was made in the outer part of our solar system, and it is a icy world, and therefore, because of its interaction with Jupiter's gravity field with tides, we believe a lot of that ice is melted, and inside that beautiful moon, Ganymede is probably an under ice crust ocean. And we believe the ocean's pretty big, may have more water than we have here on Earth. So ESA has this fantastic mission called JUICE, which is Jupiter Icy Moons Explorer. And it is planned to be launched in 2022 and will arrive at Jupiter in 2029 and begin orbiting Ganymede soon after that.
Well, let's talk more about season 2. We're calling it mind-blowing science discoveries, things like exoplanets, frozen geysers on Europa and Enceladus, and gravitational waves. You may have heard about that. And recently we had this Rip Van Winkle kind of spacecraft story. It was called Image. Jim, you were a scientist on that mission.
Yes, I
was thought to be lost and phoned home recently after 13 years. I can't wait to hear that story.
Well, I'll say one thing about it, because Image was orbiting the Earth in the Van Allen radiation belts, and one day it didn't call home. And that is indeed because we believe the radiation belts really clobbered it. And the fact that it now came back to life is just remarkable.
It's a great story. And we'd also like to ask for your ideas for future Gravity Assist podcasts. So how can we do that?
Well, you can send us an email at gravityassist@nasa.gov. So I really appreciate all your help in pulling these together for me. It's I can't do it myself, and having you interview me as a person behind the scenes has just been a delight.
Well, thank you for being my Gravity Assist.